trying to turn it on, or come, it's going off. It's on now. No, it's off again. Yeah, can't have it. I don't know. So I just turn it on, I let go. So it's going to turn off again. So welcome to see me. It's not going to show anything. Anyway, so welcome. No. So today's date is 16th of January 2026. Time is now 11:02 p.m. So this is me for journal. So basically, I'm sure you key me R to get a minimal viable product of my human rights operating system because it's this. But from a problem address, the problem line is making sure open access. This problem is this Collazzt conjecture. So this is a Collazzt conjecture. This is basically the simplest unsolved algorithm. I love this kind of rollout thing because it's going to be secure by design. You say we go to this something falls down at the mathematical level. So basically, this Collazzt conjecture. You just watch the video and I'll pause it halfway.
The simplest problem in mathematics that nobody can solve.
Not yet anyway.
Here are the rules. Pick any positive number. If it's odd, multiply by 3 and add 1.
Multiply by 3, add 1.
7 becomes 22. If it's even, cut it in half. 22 becomes 11. Repeat forever. Where does it all end? Let's follow the number 7 on its journey. 7. Odd times 3 plus 1, 22. Divide 11. Odd, it shoots up 34.
So 7. So we get a calculator here. 7. 7 is the odd number. Odd plus even. 7 is an odd number. Plus 1. 7 times 3. Equals 1 divided by 2 is 1. So 1 divided by 2 equals 1. Plus 1 divided by 11 is just half it. To 1. Wait.
4. Even down to 17. Odd again. It peaks at 2 becomes 11.
So it's n. So this so n the power of n equals 3n plus 1, and if n is even, you divide by n by 2. So basically, this is secret by design. So I'm gonna watch this video and watch it fail. I'm gonna show you what I mean. So what I'm saying to you here, guys, if you don't understand the problem, how to formalize it, you're gonna have hypothesis for it because I'm hypothesis solid and grounded in them. But I don't want you to give my hypothesis. I want you to show you my hypothesis very informally. So this is 3n plus 1 if odd, and n divided by 2 if even. So this is like piecewise elimination. But the rule is the functor, and the functor is basically a transition. It's not like if n equals 0. It's not like a it's not one. This one's dynamic. It's dynamic because you are putting rows that can be derivative, odd and even. But it's a classifier. So I'm telling you, this is a piecewise functor classifier. So the classifier of odd and even numbers are really just weighted. So 2n plus 1 is an even number. Any number n, 2n is even. Any number 2n, and then 2n plus 1 is odd, or 2n minus 1 is odd. So if you get that inclusion, 2n, because it depends. You want to kind of if it's 2 integers mapping to a positive integer. But the kind of open definition of this framework is that the idea is 2m is an axiom for an even number, and you can do 4 times 2 here. 4 times 2, 4 times 2, and that'll be 8. 3 times 2, 6, or even 1 times 5. Wrong, odd. So this number, so basically 3n plus 1 represents the 1 plus times 5, but 1 is not, this is what, the arbitrary is 3n plus 1, and 1 is odd, but it's not odd. This is the odd number here, but it's not following the rule. So the classifier is the functor. The function of maps even number via the MMUKO disjoint presupposition. I'm trying to use this problem to give some kind of geometrically net, like the net of a cube, net of something that's basically the net of a signal from the inside out. Like what is the net of some kind of signal? What is the net of a cube? The plan. What is how many? So you have 5 faces of a cube. You have let me search faces of a cube. Faces of net faces of geometry. Geometry, 3D polygons. So this will be polygons. So these are the nets here. So the nets are these things here. Yeah. But I'm trying to get it properly. So the images represent what I'm going for, but it's basically this is one example, but it's not really showing this example. So this was so because this is a cuboid, this is a cone, but there's kind of we can fold it in. So 6 faces, 12 edges, all faces are squares, and a dice, row 1, downside box. We've got the cones, but we don't know the faces, but but we don't, the faces are 1 base, 2 triangle, 2, that's kind of this is not really the net. So I'm looking for the nets. I'm looking for the net. The net. So you see the cube. So the cube is a T. The cube of a cone. So the nets are really just what you fold in somewhere to make the shape. Shape in every way, shape, or form. But you get a formula to do it. So the surface area. The thing is that you have kind of principle to fold it in. Because you're folding. You rotate it. Dimension. You move the dimension inwards and outwards. Every way, shape, or form. You have that. But the goal of this video is not to record this, it's just to use this framework to do it, which is Collazzt Conjecture. Okay. The Collazzt Conjecture represent kind of so what I'm saying is this function is like what's considered a set 3n plus 1. This is just like odd, so anything that's odd can be evaluated by 3n plus 1, and that's so this would be odd numbers. So if it is in any kind of shape, I'm going to give it a shape of something, a shape of some kind of structure, and it's an odd type or odd kind, and that kind is a class of number. Because you got token type, token value, and token kind. Token type, token value, and tokens. Token type, token value, and token memory. The memory has. So I can tell what is the type. Is a type, token type. Type of token, or is it a token kind? Is it kind of is it its relationship to the token type, or is it a type of token, or is it kind of a token? Is it a cat or dog? Is it kind of wildcat? Is it kind of wildcat? Is it type of cat? So you go, if it's a type of odd number, can you have derived odd numbers from this thing? It's a shape odd. I can think about the shape. So you got a structure of a number, which is the formula, but it's a shape. So you look the formula. So you get like so you can use the measuring units. If you get like 1, 2, 3, 3, number 3 in tally, that's your symbol. That's like 3 symbols, but I mean 3. But you got the literal number 3 in English, and you got the Roman numerals 3, I. You get that translated to 3. We have to have the signal. You have to measure them as signals. So so basically how I did it before was literally just take the number 3 and give it a shape. So think of them as geometry. So number 3 has a shape, and you have to take the surd of 3. What's the surd of 3? So you have to take the surd of 2. 3. If you get 3, so 3 is expressed as minus I, minus minus 1 square root to the power of 3. It's the power of 3. And now be to the power of 3, because minus 1 square root equals I times I. You get minus 1, so if you get minus 1 equals I times I. So you're going to get minus 1 to the power of 3. So, and then, so minus 1 to the power of 3 is minus 3. But you don't have much. You have to make this positive. So to make it positive, you have to take the square root of it. So you have to now take the square root of negative 1 to 3, negative 1 to the power of 3, and that will give you positive 3. And that will say, so this will be what you from this past way. Negative 3, you go this is a signal, which is the kind of imaginary units, which are I. So let me just try to find.
Repeat forever. Where does it all end?
So basically, let me just find the imaginary units table. These are complex numbers you're working with, so this will be easier for me to work on. So these are imaginary numbers. So I'm assuming to tell me imaginary units describe the shared trait of the what is the shared shape of what is the unit measurement of the numbers, imaginary units. So I'm going to type imaginary numbers, but I mean imaginary units. So imaginary numbers table. So I bet so the imaginary numbers are here, but the use for Secuirty. So you get so you say calculator. So this math is fun. So you get minus 2 equals to 2 equals 4. Because so you get square root. So you get so you get a solve x plus equals 0. So you get multiple sets. You get some kind of a quadratic equation. Ax squared plus bx plus c equals 0. So you get the geometry integration properties. So you get 1 times I. So you get minus 1. Minus 1 times I is minus I. Minus I. So you get minus I to the power of 3. And that will be minus I times minus I, which should be 1, and which should be negative 1. So that will be to the power of 3 will be negative 1. And negative 1 is the power of 3. To the power of 3. And that means that's not true. So you get 3 at the third, just get the square root of negative 1 to the power of 3. And that will be so I to the power of 3 is negative 1, but I'm looking for negative 3, so that's the square root of I to the power of negative 2 to the power of negative 3, and that will give me negative I, negative 3, that will give me 3, that will give me, so that works in that way, so the mapping of this usually, we're going to have some kind of foundation, offer, create, and destroy, and what should be focused on and destroy, and the collector to the bring forward because they have some kind of function you can define, you can store as this is collection over time.
Land. Let's follow the number 7 on its journey.
7.
7. Odd times 3 plus 1, 22. Divide 11. Odd, it shoots up 34. Even down to 17. Odd again.
Okay. 17, so I'll try 17. 17 plus 1. 17 times m. 3n. 21 divided by, because it's even, no, because it's odd. 21 times 3 minus 1. There's a good wrong here, but it works the same way, but
It peaks at 52. And then it falls. 17 steps and it reaches 1. Look at that journey. And once it hits 1, it loops forever. 4, 2, 1, 4, 2, 1. Every number gets...
So basically the 41 thing is like, it has to be, everything's before to come out category. But what is that category? What's the shape of that? What's the shape of 1? Unity, 1. So that 1 is not meaning 1. It means it's a function. It's not a function you can try to think, to try to use some space you always have. And that's why the concept basically 41 from the number, what number was it? 4, just like, it's just like, it repeats that way forever. So I can do more because there's one of you have some space, you can continue to book your colors and you can look at your colors and say, okay, thank you guys. And we just find if you do more this video, thank you. So the goal of the is just the video, guys.
Gets pulled into the same place. Watch, a train of numbers all falling toward 1. The black hole of mathematics. 27 takes a wild ride, 111 steps, peaking at over 9,000. But it falls. 97, even longer, 118 steps. 871 climbs to nearly 200,000. Still falls. What about a billion? It falls too. This is the Collazzt conjecture. Every positive number eventually reaches 1. We've tested numbers up to 2 to the power of 68. Every single one reaches 1. But nobody can prove it. The legendary mathematician Paul Erdos said, mathematics may not be ready for such problems. Is there a number out there that escapes forever? 2 simple rules, 1 mysterious destination. every number falls. Or does it? The Collazzt conjecture.
So basically, I believe conjecture is like, I believe it's because it's some positive numbers only. I believe it is true, so I do want a picture of it, but this only works in positive numbers. It doesn't work in anything, but please have a positive shape. But you can still look positive and act positive, but it's not positive. It can be, and that's what fools people, because you look at go approve, you're looking such you're such a space, you don't use your computer to check the signal, and that's what I'm saying. This is what I'm saying. You just check what is there already, and the signal I'm talking about is the marginal units I'm talking about in the framework of Kubernetes.
The simplest problem in mathematics that nobody can solve.
So this is just stop it now.